So we're going to start our discussion of probability, where math classes often start with some definitions. We're going to define an experiment to be a procedure that produces one element from a set of possible outcomes. The sample space is the set of all of those possible outcomes, and an event is a subset taken from that sample space. Okay, very theoretical sounding. Let's look at an example. I think that'll make some of this clearer. So let's say we define our experiment to be rolling a single die. Then the sample space is all of the possible outcomes of doing that. Well, we're assuming this is standard six-sided dice, which means the sample space is the numbers 1, 2, 3, 4, 5, and 6. And an event is any subset taken from that set. So some examples of events would be these three sets here. And if I wanted to describe these in English, I would say the first one is you roll a 1, the second is you roll a 2, and the third would be you roll an odd number. Right, so yeah, it's possible for our events to be, not just individual outcomes. They can be groups of outcomes. Okay, so this formula here, it really is the fundamental formula in all of probability. 98% of what we do from here out ultimately is going to derive from this one formula. All right, so what we're going to assume here is that S is a finite sample space. Yes, you can do this with infinite ones. Formula is a little different, but since we're doing this in the context of a discrete math class, we're going to restrict ourselves to finite spaces. And we're going to assume all the outcomes are equally likely. With that die rolling example, every number has an equal probability, equal likelihood of being the one that ends up on top. And we're going to assume that E is an event. That is, as we said, a subset of the sample space. Then the probability of E is just the size of the event, cardinality of the event, if you want to be technical set theory terms, divided by the size of the sample space. It's just that ratio. Okay, so that's all well and good. Let's look at some examples, see how we can use this thing. So I want to know what's the probability of rolling a 7 on 2 dice. Well, we need to know two things. We need to know the size of the sample space and the size of the event. Well, the size of the sample space we can get using our counting methods. I'm rolling 2 dice, which means I have 6 possible outcomes on the first one and 6 possible outcomes on the second one for a total of 36 possible results. So that is the cardinality of the sample space. Now, how about the event? Well, here, there's nothing hugely elegant about this. I literally just kind of sat down and worked through all of the possible ways that we can get two numbers from 1 to 6 that add up to 7. And I got this list here. So the size of the event set is going to be 6. So that's all I need. The probability of rolling a 7 is the number of 7s, number of ways to get a 7, divided by the total number of possible outcomes. That's 6 divided by 36, or 1/6. Okay, so let's try one that's a little more complicated. In a lottery, players have to match 4 numbers chosen at random from a list of 40. And I want to know what's the probability of winning, assuming that the order in which the numbers are chosen doesn't matter. We got to answer the same two questions. Size of the sample space, size of the event. Okay. Size of the sample space. We're choosing 4 numbers from a list of 40, and the order doesn't matter. That's a combination. So 40, choose 4. Get out the formula, your calculator, whatever. That comes out to 91,390. Now, I want you to think about this for a minute. What is the size of the event space? Well, the event is you choose the winning combination. Right? How many winning combinations are there? Well, there's only one. Right? There is one set of 4 numbers that constitutes a win. Again, remember, because the order doesn't matter. And that's all I need. Right? That's all I need to get the probability of winning. It's 1 divided by 91,390, which is, yes, a very, very small number. Okay, so how about this one? We're really kind of going through all the standard tools of probability. We like to do questions involving dice. We like to do questions involving lotteries. and we like to do questions involving decks of cards. Those are all great physical tools to illustrate all these probability concepts and formulas. So I got to do the same thing here, right? Size of the sample space, size of the event space. Size of the sample space, I'm going to choose 5 cards from a deck of 52, and the order you dealt the cards doesn't matter. So 52 choose 5 is just short of 2.6 million. All right, now the event space, this is where things get more interesting. Right? This is what it comes out to. And let's take a minute, break this down and see where all these pieces come from. There are 3 choices that we need to make when thinking about making this 4 of a kind hand. First, we have to choose the number that the 4 of a kind is made up of. Is it 4 aces? Is it 4 tens? Is it 4 kings? What's the number? Then we have to choose the suit, hearts, diamonds, spades, or clubs, for each of those 4 cards. And then we have to choose the 5th remaining card, with the caveat being that 5th card can't match the rank, the number of the card that's making up the 4. Okay, so let's look at the pieces now. This first part here, that's choosing the rank. There are 13 possible card values, ace through 10, plus the jack, queen, and king. So I have to choose one from among those 13. How about the suits of those cards? Well, I have 4 cards, and I have 4 suits to choose from. Right, so this middle part, 4 choose 4, yes, that comes out to 1, because there is only one way to do this. That's where we're choosing the suits of the cards. And then this last part is choosing the 3rd card. We've already taken 4 cards out of the deck, the 4 cards that make up our 4 of a kind, which means there are 48 cards left to choose from, and I have to choose one of them. So the total number of ways to get 4 of a kind in a hand of poker, which is essentially what we're doing here, is 624, and that's enough to get the probability. Right? It's 624 divided by that 2.6 almost million number, comes out to 2.4 times 10 to the negative 4th. Again, not very likely that you're going to just be dealt 4 of a kind. Okay, so hopefully you've got an idea of this basic formula, some of the ways it can be used, some of the basic tools that we use to illustrate these concepts. In the next lecture, we're going to look at some basic axioms of probability. We're going to lay down some rules the probabilities have to follow, right? And then we'll continue building on those tools to do some more interesting things.